in earlier discussions, we have discovered almost all points of this chapter 1 of this atomic and molecular spectra, and today we are going to see the last topic of this particular chapter, that is the atomic excitation and atomic spectra. Now, what this particular thing is, that connected with that, we are going to see one very important experiment. That is called as, the name of the experiment is Frank and Hertz experiment. This experiment theoretically, whatever, practically proved the existence of stationary orbits, the orbits which were thought upon by Bohr, the orbits that were thought upon by Sommerfeld, as well as the orbits or the stationary orbits of which we are having this principal quantum number n is in our earlier discussion we have thought these all orbits. So such type of stationary orbits are there. So what theoretically predicted and what theoretically put upon, this was explained and it was proved by this experiment. So that experiment also we are going to see, and one or two problems, if it is possible, we will go for that. So before going for this first thing, that is the Frank and Hertz experiment, we will go for the first discussion of this atomic excitation and atomic spectra. Now earlier we have seen this excitation can be caused by two different ways. Okay, so we can write here if you want, atomic excitation. Atomic excitation can be carried out by two ways. It can be carried out by two different ways. Different ways. Now what is this first way? Is very simple. It is just that is excitation by collision. Excitation by collision. Okay, so this is what exactly happens in the discharge tube. Gas discharge tube is this. Okay, or tube what we use here, which has this type of excitation. So this is what there is some particles like electrons. These particles strike with this atom. This is the atom here. It's a nucleus. This is the nucleus, and this is what an electron for an hydrogen atom. If this electron is excited to a newer orbit, higher orbit, and this goes here, and thereby the energy of this coming electron is taken, and this electron goes into the higher orbit. So this is called as atomic excitation. So somehow, if this electron is brought here, it is called as excitation, and when it comes down, this is called as a de-excitation. So this is the process of excitation. Remember here, this energy of this incident particle, maybe any other particle also can be taken, but the particle should have this energy should be equal to the energy difference between these two orbits. So if it has more energy, then this electron go in the second orbit, third orbit, fourth orbit, and so on. So this is the process that is called as excitation, and when this excited electron comes into the ground state again, so that if it is equal to n equal to 1 and this is n equal to 2, so this simple picture shows you that is the excitation and de-excitation. Sometimes it is possible that if this is the second orbit, n equal to 3, third orbit, n equal to 3, sometimes it is possible to excite this electron here into this third orbit, and then this comes back and again comes back. So these two types of transitions also can be possible. So this process of excitation by collision is one of the very important process that takes place always in all discharge tube. So discharge tube are the tubes where there is provided filament which is connected to a very high voltage. So electrons or the particles are emitted, and these particles, they in their journey throughout this particular discharge tube, they collide with the electrons of an particular atom, and this electron goes into the excited state and come again in the de-excited state. So in this process there is some, whenever the de-excitation occurs, whatever radiations come out of this process, these radiations, this is called as this emission spectra. So whenever we go for this type of transition and we go for we get these radiations emitted by certain atoms or materials or this gas, whatever, in that case it is called as this atomic the process of atomic de-excitation, and the spectra is emitted in this particular case. So this is what the process called as atomic excitation and the emission spectra by this the first type, that is the collision, excitation by collision. And the second is important thing is that absorption of photon, absorption of energy, absorption of energy from photon, so here in this case, this photon, incident photon, should have exactly same energy, whatever the energy difference between first and second orbit. Again here pictorially we can draw here. This is nucleus, this is my first or ground state, n is equal to 1, so energy of this is given by E1. Then this is the second energy state, this is said to be n is equal to 2 and its energy is E2, and I know this difference between these two, this difference is given by h nu is equal to, okay, I'll write this in better words, this is going to be h nu is equal to E2 minus E1. So what is difference between these two? So if I write this, since nu is can be written as C upon lambda, therefore I can write this expression as herefore h into C upon lambda is equal to E2 minus E1. So wavelength of this radiation of the photon, or the energy of the photon, should be exactly equivalent to this or equal to this. Then there is a chance whenever this photon comes, so this photon of certain energy comes and this photon is absorbed and this electron goes into the higher state, so this is called as the excitation, and whenever it comes back again to the ground state, so it is called as de-excitation. And in this process, whenever we go for this process, there are two different types of spectra are possible. One is called as absorption spectra and second is called as the emission spectra. So in case of emission spectra, as I discussed, the electron from higher orbit comes to the lower orbit or lower energy state, and thereby certain amount of energy is radiated in this process. Whereas if a particular complete white light of several different types of wavelengths is emitted, here in our book we have drawn this diagram, different types of these photons are coming. Okay, I am showing their wavelengths are like this. So all different types of wavelengths, these photons are coming. This is the nucleus or atom here, and this atom gets excited. Some of the radiations are absorbed and some of the radiations are not given out. So one of the radiation is found to be absent here. So this particular thing is found to absent, that means it is absorbed by this. So this electron inside that atom goes in the excited state, and therefore in its spectrum we see this particular photon or this particular electromagnetic radiation is absent, and therefore if I go for its picture of the spectrum of this in a slit, you'll find that all radiations are present, okay, except few radiations which are being absorbed. So actually I could have shown these different types of lines are possible, and some of the lines are found to be absent in the region. So this type of spectrum is called as absorption spectrum. So in the output or in the spectrum, the radiations which were, that means if it is seen here, if this spectrum is seen, you'll find that all lines are present there before this interaction happens, and after the interaction some of the lines are absent, they appear somewhat dark as compared to the other background, and this type of spectrum is called as absorption spectra. Whereas if the element itself is there and if it is radiating in its energy, its emission spectra will be exactly this. So the line which is absorbed here, this line will be again emitted here, and this is what an emission spectra. So depending upon the different types of transitions from which orbit to which orbit, different types of transitions are there, different types of lines are possible. So this is called as this emission spectra. So emission spectra and absorption spectra, the lines are exactly same. In one the radiations are emitted, in one the radiations are being absorbed. So this is the concept of this origin of the emission spectra and absorption spectra. Remember, this is the basic concept that is used in physics, or that is known by physicists just by before 100 years or like that. So this is the way with which we are able to see different objects That means whatever happening around us, whatever objects we are looking around us, here the radiations are incident upon that material. Some radiations are absorbed and some radiations are emitted. That means the tree leaves of the trees appear to be green, blackboard appears to be black, something else. Now this particular board is appear to be something of a color, that is maroon color as shown here. Now what happens in this case? Whenever the certain light radiations are incident upon this object, all radiations are being absorbed and only maroon radiations are being given out. That's why I am saying this board is a maroon one. Or leaves of the, as leaves I have said, of this any tree, that appears to be green, because in that particular case all the radiations, all the photons which are being falling on this particular leaves, almost all photons are absorbed there, and only green photons are emitted, or green radiations are emitted, and that's why this appears to be green. So whatever things we look around us, okay, every day or every moment, this particular phenomenon of excitation and de-excitation goes on, and thereby we observe different types of objects very easily. Now you'll find that in dark we cannot see this particular object, whatever may be its color, because म्हणजे अगदी मराठीत सांगायचं झालं तर अंधारात एखादी वस्तू ठेवली तर ती आपल्याला दिसत नाही, म्हणजे त्याच्यावरती जर कुठला लाईट रेडिएशन पडला नाही, हाताने तुम्हाला ती समजेल, पण डोळ्याने ती दिसणार नाही, कारण इट रिक्वायर्स रेडिएशन्स टू बी फॉल अपॉन इट, and some of the radiations are absorbed, some of the radiations are emitted. Which are the radiations which are emitted, that is we call that to be color of that particular object. So we see, म्हणजे आपला कुठल्याही गोष्टीकडे बघण्याचा जो प्रकार आहे किंवा जी पद्धती आहे किंवा जे फिजिक्स आहे त्याच्या मागचं, this is the physics that we see actually spectrum of that element. So emission spectrum is seen, and actually there is absorption spectrum too. So absorption spectra and emission spectra of any of the element, okay, I am talking element, not of any object I am saying here. So that is found to be exactly similar. So in next all our derivations and all chapters, second, third, fourth, etc., every time we are going to come across this concept of this spectra, emission spectra as well as absorption spectra. So in laboratory you might have seen sodium vapor lamp. We have called already that the sodium vapor lamp dominant lines are D1 and D2. So these lines are emitted when this sodium atom is excited to highest energy state, and whenever these electrons of sodium atoms come down from higher energy state to this lower energy state or its ground state, in that case sodium lines. Along with that there are several other radiations are there, but the sodium D lines 5890 and 5896 angstrom, these lines are very dominant, and that's why the color of the sodium vapor lamp is found to be of that particular color which we see on the road. On the other hand, mercury spectrum is bit different. That is also you have been observed in earlier in SYBSc or HYBSc how mercury spectrum looks. So this mercury spectrum has 6-7 different lines, yellow, violet, green and so on, and each line has its own frequency as well as own wavelength, and this is the signature of that element. Now no other element in an physics or in anywhere which will have exactly identical spectrum like mercury, or spectrum of hydrogen is totally different, spectrum of oxygen is totally different, spectrum of any other element, if it is carried out or if it is seen, then it will be found to be different. So this is how the theory what predicted and what we have we are being observing, that is these things are again matching. So that is what I said in the beginning of also, that every element has its signature spectra. So that is the signature, identifying its spectra we can identify this type of element. So apart from chemistry, this is one more tool that science has found. From spectra itself we can identify the material. So in chemistry we do analysis, inorganic or qualitative or whatever type of organic analysis, and in that case we identify different types of metals and non-metals present in the given sample by chemistry way. In physics way or in spectroscopy way, just observe the spectrum of that particular material, and either absorption spectrum or emission spectrum, and that also we can find out from that spectrum, studying the spectrum, which lines are present, which lines are not present. This vector atom model can directly predict what that type of elements are. So this is one forensic tool or analysis tool where which this absorption and emission spectra plays a very vital and important role. So this is one very important achievement of this theory, vector atom model and all this atomic spectroscopy and so on. Now let's go next to the one of the experiment that is called as Frank Hertz experiment. Frank-Hertz experiment. And remember, this is important from the examination point of view. Always खरं तर आपण आतापर्यंत पाहिलेले जवळपास सगळेच मुद्दे तसे खूप महत्त्वाचे आहेत टू अंडरस्टँड द बेसिक्स ऑफ दिस ॲटॉमिक अँड मॉलिक्युलर फिजिक्स. बट दिस इज वन मोर एक्सपेरिमेंट which strongly supported this hypothesis, which was put upon by Bohr or Sommerfeld or some other scientists as well, that there exists this atomic orbits, stationary atomic orbits. So this was proved by this particular people based upon the following experiment. So we will just draw a diagram here to show what actually this experiment is, and based upon that we can go for the actual analysis of this experiment. So this is one tube, vacuum tube is shown to be here, and here in this particular tube there is a gas, some gas is filled in, and now there is one filament as shown there, and this filament is being connected to some potential, some positive negative, some low potential as shown by this, and it is at the same time this is connected to further with a very high voltage, negative positive negative positive negative, and like that. So very high voltage is provided here. In between this is connected to one such plate. This is called as a plate. This plate, and this plate is connected to the positive of this battery, and in between there is one such this is positive and this is small negative, and in between there is one, this is called as grid. Okay, so this is a grid, this is vacuum tube in which is low density some material is kept there. This is filament, then these are the sources, this is V and this is V0. So potential across this grid and this plate is V0, and potential across this filament and this is given to be V. V is said to be very very large as compared to this V0. Now why grid is used? So whenever these electrons, when these electrons are emitted from this filament, this electron travels, and in between this electron carries the ionization of the molecules or atoms of the gas which has been placed in this particular tube, and some of the electrons can reach directly to the plate, and thereby this gives a certain current here. So if some ammeter is provided here, minus and plus, certain current is shown in this particular circuit, and this current can be measured, and we can find as increasing this potential, positive and negative, this current goes on increasing to a certain level, and then it abruptly falls to a very low value. So what is happening, why it is happening? If this type of things are understood, then we can go what happens inside this electron and the atoms here of this particular gas. So this excitation de-excitation phenomenon takes place, and thereby actually excitation phenomenon takes place, and that is how this particular simple experiment of this, that is called as Frank-Hertz experiment, that experiment supported very nicely to the concept of these atomic orbits or atomic stationary states as follows. Okay, so this is the diagram, you can draw this diagram. We'll write in very brief about this experiment, what actually happens and what is its interpretation and what is our theory and whether this is according to this theory or not. Okay, so Frank and Hertz experiment. This experiment was carried out in 1914. Frank and Hertz experiment. These are the two names of the two scientists. Experiment performed in 1914. You can understand. After this Bohr theory or Bohr model is put forth, then this experiment was performed. This experiment demonstrated, this is a demonstration, demonstrated that atomic levels exist, that atomic levels or stationary orbits okay, atomic level or stationary orbits exists and the atomic levels found here are exactly same as suggested by the theory. We will write this later on. Okay, that will see something later on. So this type of atomic level exists. Okay, so what is this particular apparatus? We won't show in much about this. We'll just write in short here. Here vapors of various element, one element at a time, various elements. This is a discharge tube. Various elements are bombarded with electrons from filament. Okay, and we can calculate their energy too. A small potential, small V0 is applied between grid. Grid is also a metal plate, but it has some holes. That's what is a grid. Is applied in between grid and plate. That prevent, that means all electrons are not supposed to come here. Only few electrons which is having some specific energy, these electrons will be allowed to pass through this particular grid. That's why this is what functioning of grid. That prevent electrons with less energy, then certain value to reach the plate. Okay. All electrons are not required there. Only few electrons which are having some specific condition, energy of the some specific value, these electrons will be allowed to enter there. So, and then an accelerating potential capital V is increased. So when we increase this potential, more and more electrons, now the number of electrons coming from this to this end, traveling through this to this, that goes on increasing. More and more electrons arrive at the plate. Okay, and that is indicated by current, ammeter in the circuit. That is the current, indicated by the ammeter, that is the current. Okay, now there are two situations. In one situation we can assume that whatever collisions occurs between these atoms of these electrons and these electrons coming out, these collisions may be of the two types. One is called as elastic collision, and second is elastic collisions, and second is the inelastic collisions. So inelastic collisions. So most of the times it is found that these elastic collisions do occur there. That means what? The energy transfer of these electrons is not much there. So most of the electrons, even though they have some interactions with this, some small excitation of this particular gas molecule, gas atoms found there, and almost all electrons are reaching through this grid to this particular plate as I go on increasing this accelerating potential. So in the elastic collision, since there is no absorption or energy of the absorption of the energy of this incident electron, so this particular current in the circuit goes on increasing as I increase this potential higher and higher, and then there reaches one such a stage that if this more number of electrons are as attracted by this particular potential here, positive potential here, then in one case it is observed that this particular things, it is observed that automatically, actually I have drawn this to be a, this side is negative and then this is positive. Make this small change in the diagram. This is negative and this is positive. Then this is accelerated, so it won't accelerate unless if it is made positive. So if it is positive, grid and this plate both are made positive as compared to this filament. So electrons from this will undergo the elastic collisions, and as long as elastic collisions are there, these electrons are able to reach to this particular plate, and thereby a current is shown to be increasing in the circuit, and at one stage one such point comes that most of the electrons are now completely absorbed, so no electrons reach at this particular plate, and the current in the circuit abruptly reaches to a very low value. And then again, as I go on increasing further this potential again, so second spike is found to be there. Second time again this number of electrons are found to be more and more electrons are found to be arrive at the plate, so current goes in the circuit and again it falls to a some lower value. Now this up and down or increase and fall, this must have some connection. So why this is happening? This is what thought by this Frank and Hertz in their experiment, and later on they found that this is connected to the first excitation, second excitation, third excitation of that particular gas ball atoms, which are being excited from the first ground state to first excited. Then this number of electrons reaching there leads found to be less, and then therefore current drops there. So this particular drop of the current, if I go for calculation of these energies of the electron required for that, and if I go for a particular given molecule, given atom or gas, if I go for calculation of this theoretical calculation of the energy difference between ground level and first excitation level, these two are exactly matching with each other. So actually measured, practically measured energies of the electrons which are emitted here, and the energies which are predicted by the theory here for the first excitation, second excitation, etc., that is exactly matching, and therefore there is a variation in the current, and this variation can be plotted as follows. Okay, so we'll plot this. So remember, there are elastic and inelastic collisions are taking place. So these particular things makes a very large difference, and that's why we get a particular pattern, or the alternating potential versus plate current graph is shown by a particular curve there. So we'll drop plot this later on. Before that, we have to write here something. So right, if Ke is conserved, if kinetic energy is conserved when electron collides, when this electron collides, DES collides with one of the atoms in the vapor, one of the atoms in the vapor, the electron bounces in different direction, some different new direction. As atoms are heavier than electron, the electron almost loses no Ke. Electrons almost loses, LOSES, loses no kinetic energy. This is an elastic collision, therefore no loss of energy is there, no loss of kinetic energy in the process, no loss of the kinetic energy in the process. Okay, and therefore the current goes on increasing, current in the circuit goes on increasing. So this current goes on increasing after certain critical energy is reached. After certain critical energy is reached, the plate current drops abruptly. The plate current drops abruptly. ABRUPTLY, abruptly, अचानकपणे, अतिशय वेगाने हा करंट कमी होतो, abruptly. So So this suggests at this stage, that means whenever this stage is reached, electrons are losing all its kinetic energy, and thereby they are not able to reach to the plate and no current is there. So at this stage, electrons are losing all its kinetic energy. Okay, all its kinetic energy to excite atoms, to an energy level, above its ground state. Okay, and such type of collisions are inelastic collisions. So in these collisions, almost all the kinetic energy of the electron is lost, and these electrons are now not able to reach to the plate, and therefore plate current against this accelerating potential goes on decreasing very abruptly. And that is what, if I draw this particular diagram, again a rough diagram here, so that diagram shows you a very interesting picture here. This is the accelerating potential. So that is my V0, and this is what the plate current, that is capital I, so which we are measuring here. So it is observed in this experiment that initially this particular current goes on increasing, reaches maximum and then falls, comes down. In the second stage also, when I go for still increasing this potential, again this current reaches maximum and again falls. Then in the third cycle, again in the third step, this also goes on increasing, reaches maximum and again falls. So this rise and fall has to do something about. Okay, so these are some specific kinetic energies of the electrons. These energies are being absorbed completely, and thereby no electrons are allowed to go further from grid to the plate, and therefore the current falls. So this fall and rise of current or the plate current, it has to do something about the excitation, de-excitation of atoms, as well as the energy states of that atoms, and so on. Okay, so we'll write further. Then, as accelerating voltage is increased further. Now again, these electrons which are being accelerated, this energy goes on increasing, and this reaches to again some higher value. So it starts this region. Once it falls very low value, then again starts increasing as I increase this particular potential, and this reaches a maximum. Now this, okay, here if this plate current observed at this end and plate current observed here is much more. So why this high voltage current is here? Because most of the electrons are now again traveling towards the plate, so this current goes on increasing and reaches a new high. So that is how. Then as the accelerating voltage is increased further, the plate current again increases. The plate current again increases and fall after certain value. Okay, and further trend is again same. That means in the next of this also, if I go again still increasing this accelerating potential, further trend is continued. That means rise and fall of this plate current is continued. So we are getting elastic collisions. At one stage we are getting inelastic collisions. Whenever elastic collisions, plate current goes on increasing, and whenever occurs an inelastic collision, so almost all the energy of this incident electron is being absorbed, and now no electrons are unable to reach to the plate, and thereby a process of this particular the plate current falls very sharply. Okay, now to check now why this is happening. So for that they have done one such experiment regarding mercury, and they come to the conclusion as follows. To check whether the critical potential are due to atomic energy levels. So whether this rise and fall is associated with this, they did something very interesting. Atomic energy levels. To check whether the critical potential are due to atomic energy levels, Frank and Hertz observed emission spectra. So for different elements they carried out this experiment, once for mercury, then for sodium, then for some other gas, some other type of material, and whatever predicted values and whatever the electron energies required in this case for this fall and rise, these were exactly found to be similar or same, and that's how they supported this theory of the atomic excitation and de-excitation, and then strongly supported the orbits, stationary orbits, or whatever concept of stationary orbit, that is now completely supported here. So Frank and Hertz observed emission spectra of various vapors. Emission spectra of various vapors. Okay. For example, now they have used this particular example. In case of mercury, that is Hg, mercury, minimum electron energy of 4.9 electron volt was required to excite the 253.6 nanometer spectral line. Means what? Spectral line. So this is this typical spectral line, which is required to be energy of an incident electron to be 4.9 electron volt. So I'm just again one more picture I'm drawing here. This electron is coming here with energy 4.9 electron volts, and in case of mercury, this is ground state, and somehow this all its energy is being absorbed by this atom here, electron here, and this reaches to, this is my ground state, that is E1, and this is the first excitation, that is E2. So this electron absorbs all its energy of this incident electron, reaches here, stays here for some time, and then again comes down there. So this is what energy is taken by this electron. It gets excited, and the amount of energy emitted here, this radiation has its wavelength exactly 253.6 nanometer. So this is what I'll observe. This is one emission spectrum of this mercury has been observed for the first time, or in this case. And if I go for theoretically photon of wavelength, the same wavelength, that is 253.6 nanometer, has energy. Okay, we can calculate this energy by this formula. E is equal to h nu. By this is what Planck's radiation formula can be used here. So this is nothing but h into c upon lambda, because c is equal to nu lambda. This relationship is known to us. So nu can be replaced by c upon lambda. Now this lambda is known. I can calculate E is equal to, h is 6.62 into 10 raised to minus 34 joule seconds, into c is 3 into 10 raised to 8 meters per second. I can use all the MKs units there, and this lambda is nothing but 253.6 nanometers, means 10 raised to minus 9 meters. So if I do all these calculations, I'll get this much amount of energy is 7.84. You can do this calculation if you want. 7.84 into 10 raised to minus 17 joules. And if I know 1 MeV or 1 electron volts is equal to 1.6 into 10 raised to minus 19 joules is equal to this. So if I divide this number by E is equal to 7.84 into 10 raised to minus 17 joules, if it is divided by this number again, that is 1.6 into 10 raised to minus 19, we exactly get this number to be 4.9 electron volts. So what is the amount of energy that is required for this incident electron here? That is 4.9 electron volts, and the amount of energy that is released in the process of de-excitation of this mercury atom from first excited state to ground state is again exactly 253.6 nanometer. It is measured experimentally. This is also measured experimentally, and it has been found that these two values are matching, means that this electron in this this particular mercury atom is being raised from ground state to excited state, and again de-excited from this excited state to ground state. So thus such type of stable orbits or stable energy levels are available, and this is what the concept of this particular atomic model, Bohr atomic model, as well as vector atomic model and so on. So this particular concept of stationary orbit is verified with this particular result as shown in this particular calculation. Okay, so right here, last statement, thus the theoretical results the theoretical results agree with the experimental observations. Okay, you will get more about this if you go for reading of this book by Beiser. Okay, Beiser, modern physics by perspective of modern physics, Beiser, that has very nicely explained each and every aspect of this. So what actually explained was carried out, what were the predicted result, theoretical result, and whatever the experimental result, all its graph and etc. This is very necessary thing. Okay, so from the examination point of view, this Frank Hertz experiment is one of the very important questions. Sometimes if vector model is not asked, then Frank Hertz experiment will be asked. So in that sense, the entire derivation and its description and the diagram and its interpretation, that is one of the very important concept here. So if you want, you can write the last statement here. Thus this Frank Hertz experiment supported, proved the existence of stationary energy level, stationary discrete discrete energy levels. Okay, what is for first excitation, same thing is observed for the second excitation too. That means what is the specific spectral line that is emitted after second excitation, that was known, it was predicted, and experimentally whatever amount of energy we have provided to this incident electron and the amount of energy emitted in the process of the second excitation, these were exactly found to be matched with each other, and that's how this has strongly supported this concept of this vector atom model as well as Bohr atom model, wherein we have put this concept of this stationary orbit. So here we have finished this chapter number 1 as we have completed right from the beginning. Now for your internal examination of this which is starting from Monday, for this atomic and molecular physics, you will have only one chapter for discussion. So whatever I have already put all these particular lectures on YouTube too. These notes are I am sharing with you in the evening or maybe tomorrow, but there will be 25 MCQ multiple choice questions there, for which we have to go for solving